So let's look at an example of direct proofs in action. So this example is going to be a theorem, and I'm going to abbreviate theorem as THM because that's a common convention to do. So this is a theorem right here. Okay, so here's our theorem. For all real numbers a and b, if 0 is less than a is less than b, then a squared is less than b squared. You might recall this is the exact example that motivated why we need proofs. And we were looking at and showing how our inference rules wouldn't really help us to prove this theorem. So let's go ahead and break it down and see how we can use a direct proof to show the validity of this theorem. So first off, what we'll notice is we have right here something that's given to us for all real numbers a and b. And then this part right here, this if-then statement, this right here is the claim. And you'll notice that this claim right here is indeed of the form if something, then something else. So it really is of the form P implies Q. We're trying to show a claim of P implies Q. And so that makes me think, a direct proof might be applicable right here because a direct proof is a way to establish the validity of a claim if P implies Q. So before we had the direct proof technique, what we were stuck with is that we were given A and B are real numbers, and our goal of what we wanted to prove was this if-then statement. And we noticed that our inference rules didn't really give us any way to do that. Well, after we apply the direct proof technique, we have the following. So with our direct proof technique, what we are given, we still have A and B being real numbers. But with our direct proof technique, we also assume that P is true. And then we try to make an argument that Q is true. So in this particular theorem right here, our hypothesis of our P implies Q right here is this inequality right here. So what we are given, we are assuming that 0 is less than A is less than B. And that's going to simplify things a whole lot because then our goal simply becomes to show that A squared is less than B squared. So this shows you the power of a direct proof technique because it's given us one more inequality or one more thing to use to then try to show one simple inequality right here. So let's actually do this in a formal proof technique. So let's go ahead and take this theorem right here and write down its proof. So my direct proof technique, it starts out with all of my assumptions. So it starts out with what was given to us, say A and B are real numbers, and then you assume the hypothesis of the claim that you're trying to show. So when I wrote it down previously, this is basically our assumptions. So those are our assumptions. And what we had to do next is we had to construct an argument that showed that Q is true. And Q in this case is this inequality a squared is less than b squared. So somehow now I have to make an argument that shows that this inequality leads to that inequality. So let's see here. Well, I see this inequality right here, and I see the thing that I'm trying to show involves squares. So the first thing that I might try to do is multiply through by, well, let's say a. So multiplying through by a gives 0 is less than a squared is less than b squared. And I don't have to worry about flipping any of these inequalities because I've already assumed that a is a positive number right here. So, okay, good, that's getting us one step closer. I see an a squared right there. I also need a b squared though, so let's go ahead and try multiplying through by b. And here again, b is a positive number, and so multiplying this inequality through by b gives me 0 is less than ab is less than b squared. And so, since I have a squared is less than ab, and ab is less than b squared, I can string those inequalities together. Since a squared is less than ab, and AB is less than b squared, then a squared is less than b squared. So you'll notice that I've actually finished. I am done with my proof. And by convention, you can put a little box right here that says my proof is finished. And this right here is shorthand for QED, quod erat demonstratum. So it has thus been demonstrated, but it's just a shorthand to say my proof is finished. Why is my proof finished? Because what I've successfully been able to do is take my assumptions, use my assumptions to make an argument to then establish the truth or the validity right here of my conclusion. And so I've followed the direct proof technique of taking my assumption and assuming P, making an argument, and then getting my conclusion right here. We've already established that the reason why this works relies on that logic and understanding of the truth table of P implies Q.